Today's video is all about electron configuration, E-configs. That is the arrangement of electrons on the outside of an atom. Because any chemical reaction that we talk about in this class is the interaction between the electrons. Even everyday reactions, like the combustion of gasoline. In Bohr's model of the atom, the electrons have a fixed orbit, like planets orbiting the sun. This is not the case, right? We're crossing out this idea of a circular orbit. What we are keeping from Bohr's model is the idea that there's a fixed amount of energy needed for an electron to go from this energy level to the second energy level or to the third. We call that a quantum of energy. And in fact, electrons do not reside in between these energy levels. So it requires a quantum leap for an electron to go from one energy level to the next. Using Bohr's quantized levels, we get to quantum mechanical theory. In that, we're going to name each energy level with a quantum number, right? A principal quantum number. So energy level 1 gets the number 1, energy level 2 gets the number 2. If you think of this as a theater or a stadium, energy level 1 is going to have the least seats in the stadium. And the same thing in the atom. Energy level 1 is going to hold the least electrons. There's the least places for the electrons to reside. As you get to larger energy levels, you'll be able to hold more electrons. Here's another representation of the energy levels. We can continue with the theater analogy in that the first energy level is going to hold less electrons, the second energy level can hold more, the third more than that, and so on. What this adds to our model is these sub-levels. Okay? The first energy level has one sub-level, the second has two, the third has three. And these sub-levels hold different amounts of electrons. And they are named according to the shape of their orbital. Again, it's an orbital, not an orbit. Heisenberg's uncertainty principle tells us that we cannot pinpoint both the location and the movement of an electron at the same moment in time. So it's a probability of where the electron exists. And these sub-levels are labeled by their shapes. So the S sub-level, all the way through, has a spherical shape. Then the P sub-level will have a lobe shape, and the D has its own shape, and the F sub-level has another shape. You can see them here, at least the S, the P, and the D. We won't deal very much with the F sub-level. That was just to wake you up and remind you why we're studying the electrons, because all chemical reactions that we're going to deal with in class have to do with the interaction of electrons. So here we're back to the sub-levels, or the orbitals. The S-shaped orbital, right, spherical, that means that the electrons are moving around within this sphere, right? There's a probability where they are, we don't know exactly where. There's only one orbital within the S sublevel, so only one sphere on each energy level. When we look at the P orbitals, you can see that there's three of them. There are three orbitals in the P sublevel, where there's 2p, 3p, 4p, they have three orbitals. And this is where the electron, the probability of where the electron would reside. And then the D, you can see we have 5 orbitals. And again, these are the probability of where the electron would reside. Before we can start placing electrons into their orbitals, I have to make something clear. When I say the word atom, I'm talking about a neutral atom. That means that the number of protons equals the number of electrons. So a sodium atom has 11 protons and 11 electrons. So that means we can get the number of electrons for any atom right from your periodic table. And we're only going to deal with atoms today. Later on, once we get the gist of this, we'll start dealing with ions. This is one way to diagram the electron configuration. This is called an Aufbau box diagram. Aufbau is a German word meaning building up, because we're going to build up the electrons from the first level on to the second to the third, depending on how many electrons we have. Each box represents an orbital. According to the Pauli exclusion principle, each orbital can only hold 2 electrons. So the 1s, the whole level, first energy level, can only hold 2 electrons. Then the second level can hold 2, 4, 6, 8 electrons. And we're always going to place in the lower level first. It takes more energy to get up to the second level. So electrons will fill the first box before they go on to the second, and then before they go on to the next level. Now, even though these two are in the same energy level, the second energy level, you always fill the S sublevel first. It takes less energy to do that. Then you can fill the P sublevel. And then after the P is filled, you could go on to the third energy level, do its S and its P. Here you can see we've set up the classroom to represent part of the Aufbau diagram. This desk would represent the first energy level, the S suborbital. 2 seats, 1 for each electron because the orbital holds 2 electrons. This would be the second energy level, S orbital, because it also only has 2 seats. We're cut off a little bit here, but you'll see as we go that this would be the 2p sublevel. So there's going to be 2 seats here, and then 2 more and 2 more. So we've got 6 total seats, 3 orbitals. All right, so we're going to slowly start filling or building up the Aufbau diagram, 1 electron at a time. We had some volunteers who represent electrons. So here's our first electron. Notice that she goes straight to the 1s, right? She doesn't have enough energy to get to the 2s or the 2p, so she has to just go to the 1s orbital. You'll also notice that she is spinning, all right? This is going to become important. Remember, electrons are negative. So part of the Pauli exclusion principle is that she has to spin in a different direction than the electron that sits next to her. Here's our second electron. Takes a seat in the 1s also, because she does not have enough energy to go up to the 2s or the 2p. Now, since they're both negative, normally they would repel each other. But to stay in such close proximity, it's important that she revolves or spins in a different direction. That helps to cancel out the repulsion. Here's our third electron, jumps up to the 2s, so she's got more energy, right? The 1s is filled, the next place she can go is the 2s sublevel. She also will spin. Electron comes in and takes the other 2s position. Right? Again, she doesn't have enough energy to get to the 2p. And the 2p cannot be filled until the 2s is filled. Here's our first 2p electron. Takes her spot and begins to spin. Now, watch this. Right? If there are open spots within the sublevel, you're not going to have 2 electrons go right next to each other at first. This is called Hund's rule. So our next electron actually moves over to the next orbital. Right? Think of it, if you got on the bus and there are a bunch of empty seats, would you sit next to this first person who's sitting there, or would you choose a seat off by yourself? There is still some repulsion even if they're spinning in opposite directions. So they're going to take the orbital that's open first. Again, this is called Hund's rule. And our next electron comes in. So far we have the 1s is full, the 2s is full. So that's 1, 2, 3, 4 electrons. Then we have the 2p, and we have 3 electrons in the 2p. So far we've placed 7 electrons. Now we can fill the seats or the orbitals within the p sublevel. Right? These electrons, they don't have enough energy to go up to the third energy level, and my room doesn't have enough room. So we're going to fill up the p sublevel, and please note the opposite spins. So here we have our complete electron configuration for this atom, which had 10 electrons. We've got a full 1s, we'll call that 1s2. We've got a full 2s, we'll call that 2s2. And we've got a full 2p, we'll call that 2p6. Here's what it's going to look like for you on paper. We're going to use arrows to represent the electrons in our Aufbau boxes. Again, each box is an orbital. So our first electron we place in the 1s sublevel, right? In this orbital. And the direction of the arrow indicates its spin. This would be like if we diagrammed hydrogen's electron configuration because it has 1 electron. The second electron, same orbital because of the Pauli exclusion principle, but spinning in an opposite direction. We're going to show that opposite spin with an arrow pointing down. When we write this out, we can write it either as the Aufbau box diagram, or we can write its electron configuration, which for hydrogen would be 1s1. Helium has 2 electrons in the first energy level, so it would be 1s2. If we continue, third electron goes in the 2s, Pauli exclusion principle makes sure that the fourth electron also in the 2s. Fifth jumps up to the 2p. Then we've got Hund's rule. The sixth electron has got to go to the next orbital, right? It's not going to share an orbital unless it has to. And then the next electron does the same, following Hund's rule. Now we can double up into the 2p orbitals with our 8th, 9th, and 10th electrons. And now we have full 10 electrons. So the element here, this would be the electron configuration for the element neon, because neon has 10 protons and 10 electrons in its neutral atom. If we had more electrons, we would have to put them up to the third energy level, into the 3s sublevel, and then the 3p, and so on. There is one thing that seems a little bit out of order. When you get to larger atoms and we're filling up to the 3d, because of the energy requirements, we actually go from the 4s, so the fourth level, then to the 3d before it goes to the 4p. It takes more energy to put the electrons in the 3d sublevel than it does in the 4s. So that's why we go 4s and then 3d and then back to 4p. To recap, why are we studying electrons? Because every single chemical reaction is a reaction or an interaction between electrons, one atom and another. Even here, they're mixing two liquids, right? The liquids are starting to glow. It's a chemical reaction. They're giving off energy. That energy is being given off by the electrons. It's the electron interaction. These electrons are jumping up to a higher energy level, and when they fall back down to their original states, they give off energy in the form of light.